Welcome everyone, and thank you for joining us today. My name is Kara, and I'm with the LTAP Center here at ODOT, and I'll be your host for this webinar. Today's webinar is Evaluate Sources and Reduction Potential for Nitrogen and Phosphorus in variegated and unvariegated ditches, and we're thrilled to have Ben Phillips as our presenter. Before we begin, I'd like to cover a few housekeeping items to ensure a smooth webinar experience for everyone. If you have any questions during the presentation, please use the questions panel in your screen. You can type your questions there and we'll address them during the Q&A session at the end. If you're experiencing any technical difficulties or have any other issues, feel free to use the chat panel to communicate with our team and we'll do our best to assist you. Please note that this webinar is being recorded and the recording will be made available to all registered attendees after the session. All right, with that out of the way, let's get started. It's my pleasure to hand it over to Ben. Ben, the virtual floor is yours.
Thank you very much. And thank you everyone for being here today. I'm very excited to share this research. I've been working on this for quite a little while, and so happy to get it out there. So yeah, we'll start with the name of this project is Treatment of Nitrogen and Phosphorus in Runoff by Vegetated and Unvegetated Ditches. Obviously, I'm Ben Phillips, and if you have any questions or comments or interested in a few more details, my email is attached, and yeah, feel free to reach out. And also, this project would not have been possible without the help of Ohio State, ODOT, and the U.S. Department of Transportation. Okay, so just to get a little background here, ODOT maintains over nearly 20,000 miles of roads in total, which is a lot. And to drain these roadways during storm events, they use open channels or roadside ditches to drain the roadways, which is very effective at maintaining driver safety and ensuring that there's not precipitation pooling on roadways. However, there is often a lack of water quality consideration when they're designing these. And so therefore, they serve a purpose for draining water off roadways, but there are ways in which we can improve the water quality aspects of roadways. So roadway runoff provides a source of a non-point source of pollution to Lake Erie, which in the runoff there's excess phosphorus and nitrogen, which provides fuel for harmful cyanobacterial blooms, which have been happening in the past few decades. Once this phosphorus and nitrogen goes to receiving waters, they really cause a lot of downstream pollution issues that affects not only the quality of the water, but also the animals that live in the water. And so roadside ditches are also very connected to the stream network and in agricultural watersheds. In one study by Buchanan et al., actually over 90% of roadside ditches drain to streams. 49% of those ditches drain through agricultural ditches to the streams themselves. So that just kind of goes to show you how interconnected the drainage network is. And roadside ditches aren't their own drainage way. It's all connected in a drainage pattern. And so there's limited research regarding the nutrient load that is conveyed by roadside ditches. And so it's such a I guess ubiquitous thing in our landscape, but we know so little about roadside ditches. So that presents a challenge, and also I guess a way that maybe we can improve some water quality in these roadside ditches. So ODOT designs their standard roadside ditches with grass cover and a minimum slope of 0.25% to 0.5%. And while this is the design standard, in low-lying areas, especially Northwest Ohio, where there isn't a lot of change in grade, it may be difficult at times to get to this 0.25% or 0.5% grade just due to the surrounding landscapes. And so therefore, these traditional grass ditches in the low-lying areas may develop wetland conditions due to the poor drainage as a result of the gradual slopes along roadside ditches in places with low overall gradient. And so as a result of these wetland conditions, frequent ditch maintenance is often needed to restore the hydraulic efficiency of the ditch and ensure that it can drain water during storm events. So the goals of this research were we really wanted to understand the impact of roadside ditches on runoff hydrology, and then the nutrient loading potential. We really understand the pollutant potential of these ditches and what kind of impact they're having on receiving waters. And so we planned on doing this through a number of ways, including first starting with a spatial analysis, and then doing some roadside ditch soil sampling, and finally stormwater monitoring, so we can really get a good idea of the nutrient dynamics occurring in these roadside ditches. So our objective one was to develop a method to determine the fraction of a watershed draining through roadside ditches. Studies in the past had analyzed roadside ditch drainage in terms of a watershed. So they would look at individual watersheds and determine the proportion of area in that watershed that drains through roadside ditches. And so studies in the past have used different methods to get at this, but this is one of the studies from the Lime Creek watershed in Iowa that found around 30% of area in this watershed was draining through roadside ditches. The second objective was to understand the physical and chemical properties of the roadside ditch sediment across multiple vegetative conditions. As we talked about, roadside ditches are supposed to be grass, but obviously different, slope conditions may result in wetland conditions. So we really wanted to look at the sediment properties between these two conditions and see if there was any differences there. Objective 3 builds on Objective 2 by using the same soil samples, but performing different tests to identify a low-cost method that we can use to assess the risk of soluble phosphorus release from roadside ditch sediment. There are multiple different methods to extract phosphorus, and so for this goal, we're kind of looking at a low-cost way to assess, how much soluble phosphorus can really be released by these roadside ditch sediments. And our final goal, Objective 4, was to sample stormwater quality in a grassed wetland and unvegetated wetland ditch to assess the differences in loading rates between each of these conditions and see the impact on receiving waters. So we'll start with the research approach for Objective 1, which is, again, to develop a method to determine the fraction of a watershed draining through roadside ditches. So the software we use for this is WM Drain Farm Drainage Solution Software by Trimble Agriculture. And so this is what we use to delineate the watersheds draining roadside ditches. And we primarily use this program because it's used for agricultural purposes, such as locating agricultural drainage ditches. And it uses high resolution LiDAR data to make these smaller watersheds that are kind of typical of a roadside draining watershed. So we were looking for a program that would create watersheds with a high amount of detail, so we could really start to identify these smaller roadside draining watersheds. And so in this program, we input processed LiDAR data, and it outputs high resolution watersheds as well as drainage lines and flow direction arrows for an area of interest, so we can get a really good picture of the drainage patterns of a given area. And so now we arrive at block method. So block method is what we developed to reflect the natural impediment created by roadways. Believe it or not, but most highways in Ohio are designed with at least 3 feet of clearance between the water level and then the roadway itself. And so therefore, that natural impediment is in all roadways. And so we, instead of looking at drainage in a watershed sense, we wanted to look at roadside drainage from a roadway sense. And so therefore, our blocks are an area that is bordered on all sides by roadways, as you can see below. And then in WM Drain, as I mentioned before, we use the LiDAR data and crop it to the block to reflect the block boundaries. And so if you're still a little confused on what a block looks like, transition here. If you just see this black box around all sides, important thing to note about blocks is there's no roads intersecting them. And so it's just, one piece of area with roads on all sides, and that will help us, determine what is actually draining roadside and, reflecting more of how the roads are designed. So in WM Drain, we then generate watersheds using the LiDAR data. As you can see here, that's nice and brightly colored, and really gives you a good idea of what watersheds are draining where. And so after we get these watersheds, then we get generate drainage lines and flow direction arrows based on the LiDAR points, and that will help us assist in the roadside watershed delineation. So there was a 3-step process that I used to delineate roadside draining watersheds in WM drain. And the first step was to only include watersheds with drainage lines flowing parallel to the roadway. This is the primary rule due to the fact that roadside ditches are designed at constant depth parallel to the roadway. So it's pretty easy when you see a drainage pattern that mimics that and is parallel to the roadway. It's pretty easy to tell that's a roadside ditch just because that's how they were designed. So as you can see in the figure here, it's just easy to tell it's directly following parallel to the roadway, and that's a easy indication that that's a roadside draining watershed. So for number 2 is to exclude watersheds that drain perpendicular to the roadway, indicating flow into a culvert or outfall. So when you have these large watersheds that are typically, draining from an agricultural field, if it is draining perpendicular to the roadside ditch, that's typically going to indicate that it's going to a culvert or an outfall, because roadside ditches can't handle that large amount of flow generated from that watershed going into a specific point. And so typically that'll indicate that there's some kind of built drainage there, just because roadside ditches, the way that they're drained, they just can't intake large amounts of drainage at one point. And so that's an easy way that we can exclude watersheds. And so the third one is to include watersheds with flow arrows in the direction of the roadway. So in some of these watersheds, there's portions that will headwater portions that will run through agricultural or run through roadside ditches before continuing to drain to an agricultural ditch. And this was also found in the paper I mentioned previously, Buchanan et al. And so our solution to this was to include watersheds with only flow arrows that we can see draining to the roadway, and then we'll include any parts of a watershed with those flow arrows draining towards the roadway. And once the drainage line exits the roadside ditch, then at that point, that's where we end the boundary for the watershed or for the roadside draining area. And so just a way to make sure that we're including all parts of watersheds that drain through roadside ditches, and not excluding agricultural watersheds that a piece might drain through. So just to make sure we're reflecting the fact that these roadside ditches are pretty ubiquitous in all types of drainage, whether that be a stream or an ag ditch. They're all connected. And so after that, we generated some explanatory variables in ArcGIS Pro in order to describe the land use and topography. And this was important just to, I guess, get an idea of, what these roadside blocks look like, maybe, what proportion of agricultural land use is there, what proportion is forested, and then, the length of the streams, the ag ditches, and then the roadside ditches themselves. And all these variables were created in order to predict the proportion of drainage, a proportion of roadside drainage in a block. And so, we can use this research to, generate a few characteristics about a block, and then that can tell us, how much roadside drainage it's receiving, and possibly prioritize it for management. And so, as I mentioned earlier, we, got stream length and agricultural ditch length and roadside ditch length. These were all generated in ArcGIS Pro. We measured stream length using the National Stream Hydrography layer. Agricultural ditch length was measured using aerial imagery and WM drain watershed maps, and those were manually drawn in ArcGIS Pro, which was certainly a very involved process. And then the roadside ditch length was measured using the block boundaries, just assuming that along the block there was roadside ditches along each side, just because that's standard ODOT procedures that each side of a roadway will need an open channel to drain it. And so using these drainage characteristics, we hope to get a good idea of how they impact the proportion of roadside drainage in a block. So to talk about the findings, I delineated 135 blocks total to assess for the proportion of area draining to the roadside ditches, and then use the corresponding explanatory variables to create a regression to explain that proportion draining. The presence of a highway adjacent to the block was the strongest positive predictor of the proportion of area draining roadside. And then block stream density, roadside ditch length, and drainage density were all positively correlated with the proportion of area draining roadside. So basically what that indicates is that when you have a highway, which is typically designed with a greater level of service, so its roadside ditches are designed to convey more flow and therefore are generally larger. And so this may, be the reason that they were correlated with a greater percentage of area draining roadside in a block. But it just gives us a very easy way to identify blocks that are receiving a large area of drainage and should be prioritized for management based on that large drainage area that these roadside ditches are receiving with highway adjacent next to the highway adjacent blocks. In terms of block stream length, roadside ditch length, and drainage density, they were all positively correlated, and we'll use those in our recommendations to try to identify areas that will give us the biggest bang for our buck management-wise. So yeah, it's just a table to summarize some of the findings here. Talked about agricultural land use, forested land use, developed land use. As you can see throughout all blocks, the agricultural land use was, by far and away the highest proportion of land use, which is not really a surprise at all. A lot of these blocks were delineated in Northwest Ohio, which is very, very high in agricultural land use. So none of that is too surprising. But to focus on the proportion of area draining roadside, I mentioned highway adjacent blocks were correlated with a higher proportion of area draining roadside. And so highway adjacent blocks average 17% per block area draining through roadside ditches. And so compared to a block that doesn't have a highway ditch adjacent, those blocks only average 9.5% area draining through roadside ditches. And then so in terms of drainage density out of streams, agricultural ditches, and roadside ditches had the greatest density per block compared to agricultural ditches and streams. So in conclusion, the greater stream length was correlated with a higher proportion of area draining roadside. And so if we think about this, correlation is likely as a result of the intersection between roadways and streams. So when a stream crosses a roadway, that necessitates a hydrological connection between the roadside ditch and the stream, because you can't run a ditch through a stream. And so at those points, there's always a connection. And so, that may lead to the fact that there's, greater stream length leads to a higher proportion of area draining roadside due to that connectivity at points where streams cross roadways. And so I talked about using a regression model to predict the proportion of roadside drainage in a block. And so the final deviance explained for that model was 0.56. And so in terms of recommendations, so the block method can be used to identify large areas draining to roadside ditches and prioritize them for management. Highway adjacent ditches with multiple stream crossings are likely to drain a larger proportion of the block. And this is due to, as we discussed before, highways having a positive correlation with greater roadside drainage, as well as stream length having a positive correlation with larger amounts of stream drainage. So pretty much just combining variables that have a positive impact on stream drainage and using those to find areas where we can prioritize management. And so, yeah, these conditions are optimal for the treatment of the maximum amount of runoff reaching an outfall. And so, we can identify areas that will help us, treat a large amount of runoff that's coming onto ODOT's right-of-way. And then, so as you can see, again, clear difference in the figure between the presence of a highway, yes or no. As you can see, again, obviously, the presence of a highway is correlated with a greater amount of proportion of roadside drainage. So just, I guess, easy thing to, I guess, glean from this. Okay, so moving on to objective 2, we want to understand the physical and chemical properties of roadside ditch sediment across multiple vegetative conditions. And so we talked about wetland roadside conditions earlier. And so we wanted to take the different roadside conditions, the typical ODOT grass conditions that they would have in a roadside ditch, and then these unintended wetland conditions. And we wanted to compare the sediment between the two to see if there's any physical or chemical differences. And so by doing that, we extracted soil cores from each condition and separated each soil core into 5 centimeter or roughly 2-inch segments in order to assess the physical and chemical properties by depth. So in order to identify these sites for sampling, we looked for the presence of broadleaf cattail in roadside ditches, which would be indicative of a wetland condition. We use this logic because broadleaf cattail is an obligate wetland species, so which means it occurs in wetland conditions 99% of the time. And so therefore, by identifying this obligate wetland vegetation, we can use that to identify wetland conditions themselves. And so after we identified a wetland site, we then selected an upland or grass site by moving slightly up gradient from the point where the wetland vegetation transitions from wetland to grass. And so you can see I have a few examples here of where the start of grass conditions and the end of wetland conditions. And so that just kind of shows you the interface we were looking for to get our two types of samples at each site. So we'd get the grass sample from obviously the grass condition up gradient from the wetland condition. So each of these sites we need that transition area so we can be able to compare them accurately. Okay, so in total, we sampled 10 roadside ditch sites. And so at each site, like I said before, we took a soil core from the wetland condition, which we identified using aerial photography, and then moved up gradient and extracted a soil core from the upland condition. And so my handy dandy 3-inch by 1 foot serrated PVC pipe was used to do this. And so as you can see, very high-tech setup we have here. You put a screwdriver through holes drilled in it and pretty much just cut down through the sediment and vegetation until you really can't go any further. So not the most high-tech setup, but certainly very effective at extracting a representative soil core for each condition. And so, as I said before, we wanted to compare these results based on the core depth and condition. And so we wanted to compare same depths of the two different conditions, as well as different depths of the same condition. And so we wanted to do that to see how each condition, how their sediment differed as you move down the soil core, as well as take the same depths from the wetland and upland conditions and see how those physical and chemical properties vary at the same depth. As a result of this, we found that accumulated sediment in wetland ditches ranged from 0 to 4 inches on average and exhibited very different chemical and physical properties compared to upland soil at the same depths. And as you can see in these figures, interfaces between the deposited sediments and the original constructed surfaces were easily visible in the soil cores. And as you can see, the white line separating the two types of soil in the figures gives you a really clear idea of where the constructed sediment is versus where the accumulated wetland sediment is. And so for me personally, whenever I pulled the first soil core up, it was a little shocking to see that there was such a drastic difference. But it goes to show you how much sediment and organic matter can accumulate in these wetland conditions. Here's a table of some of the comparisons that we made by depth and some of the significant differences that we saw after we made these comparisons. And so looking at comparisons between wetland depth A and upland depth A, we can see that there's a significant difference between the amount of iron. There's significantly higher iron in the wetland ditch soil from 0 to 2 inches, as well as higher amounts of total carbon, total nitrogen, and a lower bulk density compared to upland ditches. And so then moving from 0 to 2 inches to 2 to 4 inches and comparing the upland and wetland sediment at these depths, we see again there's more iron in the wetland ditch at these depths. There's a greater amount of organic matter, and there's also a lower bulk density again. And so these kind of lend to the fact that the first 4 inches of sediment in these wetland ditches just doesn't appear to be very similar chemically or physically compared to the typical ODOT grass ditch. And so pretty much, again, wetland ditches differ significantly from upland ditches, chemical and physical properties in the first 4 inches of sediment. And so what we take from this is we can conclude that the first 4 inches of wetland ditch sediment is likely accumulated on the original subsurface. So as a recommendation, again, the top 4 inches differed chemically and physically. And so this 4 inches provides an easy sediment depth at which for ODOT to target when they do ditch maintenance events. And so, based on the difference in these chemical and physical properties, whenever ODOT goes to clean out one of these ditches, 4 inches would just really provide an easy target to dip out at, and would have some research behind it, backing out that you'd be able to, in most cases, get down to the original constructed subsurface by removing that 4 inches of accumulated sediment. And yeah, so wetland, as a result of this accumulated sediment, wetland roadside ditches obviously provide a depositional environment for sediment and runoff due to the sediment accumulation over time. Okay, so objective 3 was to identify a low-cost method to assess the risk of soluble phosphorus release from roadside ditch sediment. So taking the soil cores from objective 2, we tested them for water extractable phosphorus. So water extractable phosphorus, or also known as water soluble phosphorus, as used as a proxy for dissolved reactive phosphorus, which is lost from soils during storm events. And so pretty much what we're looking at here with the water extractable phosphorus is it's sort of a measure for how much soluble phosphorus would be lost during a storm event. And so we use the water extractable phosphorus and compare it to different soil metrics, one of which is the phosphorus saturation ratio, which uses a molar ratio of phosphorus to iron plus aluminum to assess a soil's ability to absorb P. And so pretty much what we're looking for here is to establish a relationship where, based on some given soil metric, that there's a threshold at which water extractable phosphorus begins to increase at a higher rate. And based on that threshold, that'll be able to tell us, if we look in ditch sediment, possibly above a certain threshold where ditch sediment may pose a greater risk to leaching soluble phosphorus downstream. So basically, we just are looking for an easy soil metric that we can use to establish, if sediment cores pose a risk of phosphorus release downstream. So we used hockey stick regression models in this scenario and compared soil p-values and phosphorus saturation ratios as the soil metrics against water extractable phosphorus. Typically, if you're going to do this comparison, you would use an ammonium oxalate extraction to get phosphorus and the phosphorus saturation ratio. But for this objective, we were looking to, I guess, offer a low-cost, easily available test. And so in this scenario, we wanted to compare the Mehlich-3 extraction method to the ammonium oxalate extraction to see if we could create a similar relationship where there'd be a threshold above which water extractable phosphorus would increase at a higher rate. So basically, we created these regression models, and on each side, you have a p-value telling you the significance of that slope and an r-square value telling you the deviance explained. And then so using this on each side, we're able to tell which regressions are a good fit and which relationships may be applicable in the field. And so we grouped these regressions based on the depth and the specific soil metric that we were comparing against water extractable phosphorus. And so the key relationship that we were able to glean from this objective is that water extractable phosphorus versus Mehlich-3 phosphorus from the Mehlich-3 test in the first 2 inches of ditch sediment exhibited a significant positive relationship that began at a threshold of 30 milligrams per kilogram phosphorus. And so, as you can see on the graph here, the vertical line is right about at 30 milligrams per kilogram, and you can see that starts a positive relationship at which water extractable phosphorus begins to increase at a higher rate relative to the Mehlich-3 P amounts. And so this makes sense due to other studies identifying the first 0 to 2 inches of soil as the main layer responsible for soluble P loss. So it makes sense in this instance that the most significant relationship we observed was also at 0 to 2 inches of sediment. And then so I guess looking at the typical phosphorus soil values, Mehlich-3 P values above 52 milligrams per kilogram are rated as very high in Ohio and are above optimal phosphorus values for plant growth. Then looking at Ohio Administrative Code, that states that the point sources in areas prone to algal blooms should limit their total phosphorus to an average of 1 milligram per liter. And so taking that information in and then looking at the graph we've created, we can identify 60 milligrams per kilogram of Mehlich 3P as a potential threshold above which ditch management changes are recommended based on the fact that 60 milligrams per kilogram corresponds fairly closely with 1 milligram per liter of water extractable phosphorus, which would correspond back with the Ohio Administrative Code, their limit. So basically, 60 milligrams per kilograms of phosphorus is way higher than any value you would need in the soil, and it's provides phosphorus a lot more than vegetation would necessarily need, and therefore making it a very ineffective use of phosphorus, which may lead to phosphorus being leached downstream. And so if we're able to identify sediment that has phosphorus values higher than 60 milligrams per kilogram, those provide a good candidate for ditch maintenance in order to remove that from the ditch and ensure that it doesn't get washed downstream to receiving waterways. And so in the future, we recommend that the top 2 inches of ditch sediment provides an effective measure for evaluating environmental risk of soluble phosphorus. The Mehlich 3 agronomic test is very widespread, widely available. It is low cost. It actually costs us $12.50 per sample for the study, which was very low cost, and is effective at measuring phosphorus in ditch sediment from 0 to 2 inches. And then again, a soil phosphorus threshold of 60 milligrams per kilograms provides a very simple threshold that will help make ditch management decisions and prioritize ditches that pose a risk of downstream soluble phosphorus release. Okay, so objective 4 is implementing water quality sampling in a grassed wetland and unvegetated wetland ditch during storm events. So to first identify our wetland condition, we used aerial imagery to identify roadside ditches with broadleaf cattail, very similar to how we had identified sites in objective 2. Moving up gradient from the wetland conditions, we found a grass ditch located up gradient. And then once a wetland and a grass site was selected, a nearly 700-foot section of the wetland ditch was dipped out. So pretty much when sediment and organic matter accumulate in a wetland ditch, ODOT crews go and remove that excess sediment and ensure that the ditch can operate as you would want it to during a storm event and convey the right amount of runoff. And so this is referred to as dipping out. And so you may hear me refer to it as dipping out in the future, and that's what that means. But and then once we identified these sites, we used block method to delineate watersheds draining to each ditch condition in order to inform loading rates in the future. So at each of these sampling sites, we installed 1-foot tall H flumes with stilling wells that were installed downslope of each ditch condition to receive runoff from the ditch condition in order to measure the runoff volume. And we did this using a bubbler flow module, which uses the amount of air pressure relative to the level of water in the stilling well to tell how the level of water in the ditch is changing. We used ISCO 6712 automated samplers to record the flow and collect flow-based stormwater samples during storm events. And as you can see here, 45-degree wing walls were attached to the upstream opening of the flume in order to concentrate all the flow that is moving through that ditch, in order to make sure that we're getting a representative hydrograph of runoff after a storm event. And yeah, as you can see here, stilling well, flumes, wing wall, all very important to this process. So we recorded rainfall characteristics using a 0.01 inch interval tipping bucket and also a manual rain gauge in order to get not only rainfall characteristics, but also the amount of rainfall from the manual rain gauge that had occurred since the last visit. And so every time that we got roughly 0.5-inch rainfall. I went and checked the ISCO 6712 samplers, typically within 48 hours of the end of the rainfall or sooner. And then so composite rainfall samples were mixed and processed according to each constituent's laboratory requirement. So what I'm referring to when I say composite, or where the samples were taken throughout the duration of the storm in a bucket, and then when I was going to take the samples, these samples would be mixed for roughly 20 seconds, and to ensure that the sample was uniform throughout, and to ensure that we were getting an average storm sample each time that we were taking samples. And so when I say composite, that's what I mean when I refer to that. And then so processing, depends on the nutrient constituent that you are looking for. So for example, for dissolved reactive phosphorus, in this case, we would filter that with a 0.45 micrometer filter in order to remove any sediment. So our stormwater samples, after they were collected, were sent to Old Woman Creek National Estuarine Research Reserve, where they analyzed the water quality, and then returned it back to us, where we analyzed water quality in R in order to compare the differences in pollutant concentrations and loads between the different conditions. And so hydrology data from the samplers was downloaded monthly and processed to ensure accuracy over time, and making sure that we were using the right hydrology data when we started comparing the hydrology data to the water quality data. In terms of nutrient loading rates for each site, we calculated those using both our water quality values as well as the process hydrology data. The nutrient loads calculated for each storm event was found by multiplying each storm event's event mean concentration, which we put in terms of pounds per cubic foot, by the runoff volume in cubic feet. Then the storm event nutrient loads were added together and divided by the watershed area for each site, which is again important that we delineated that using block methods so we can know the watershed area. And then the annual loading rate was then calculated by multiplying the ratio of annual precipitation to sample precipitation by the nutrient load. As you can see the calculation below. And as a result, we would get units in pounds per cubic feet per year. And that would help us get an idea of the pollutant potential of each of these different roadside ditch vegetative conditions. So to, I guess, start with some findings, a total of 64 storm events occurred over 0.1 inches during the stormwater sampling period. In total, I collected 20 paired samples between the wetland and unvegetated ditch, and 6 samples from all ditches, including the grass ditch site. And so I guess as a first thing to look at, PO4 concentrations in grass ditches were significantly greater than wetland and unvegetated wetland conditions. So if you look at this figure here, the red and black marks both represent typical values for PO4 concentrations in stormwater runoff from the black represents a wetland channel median, and the red represents the grass channel median. And so these bars kind of represent average values, and will show you kind of where these concentrations add up compared to these values that were from the International Stormwater BMP database, which uses a collection of over, I believe, 6,000 individual stormwater samples. And so basically what this is saying is that the grass ditch produced PO4 values that were slightly above values that you would typically see from stormwater in this condition. So I guess just a little unexpected that this would have a little more PO4 than the other conditions, but I guess just something interesting to glean from this. So TSS and turbidity were significantly greater in the grass ditch compared to the other 2 conditions as well. But on the other side, NO2 and NO3 conditions or concentrations were significantly greater in the wetland and unvegetated wetland ditch. And so I personally was a little shocked as well when I saw that the TSS and turbidity were slightly greater in the grass ditch compared to the unvegetated ditch. But we'll have a few explanations for that in our conclusions. But I guess from this basis, we can also see that all of these concentrations are above the black and red lines. And so that would mean that, both the wetland and grass conditions, are well above those found in the International Stormwater BMP database. So it might indicate in this, condition, these the concentrations of TSS they're receiving are, higher than you would typically receive in, a typical roadside condition. And in terms of the NO2 and NO3 concentrations, I believe that they're higher in the wetland and unvegetated wetland ditch due to the fact that there's more biological processes happening in the wetland and unvegetated ditch, which results in a lot more organic matter, leading to more nutrients and leading to higher nitrogen values in the ditch itself. So in conclusion, if we look at the loading rates, which we found using the water quality data and the hydrology data, so in the end, the unvegetated wetland ditch generated the greatest annual depth of runoff in terms of watershed inches. And so that's pretty much normalizing the total runoff over the watershed. And so if you would imagine the entire runoff for a year covering this watershed would be, for the unvegetated condition, would be about 11 inches. So just nearly a foot of water covering the whole watershed, and that's how much runoff it produced for the year. So quite a lot. Annual total phosphorus, NO2, NO3, TSS, and total nitrogen were highest in the unvegetated wetland condition compared to the grassed and wetland condition. And so this is what I was referring to in the other slide. Even though the grassed condition may have appeared to have the highest TSS values, the unvegetated wetland ditch seemed to convey a greater amount of flow, and so conveyed a greater amount of pollutants, including the total phosphorus and TSS and TN. And so that's why it's important to establish loading rates for each of these sites and not just look at the water quality data, because the water quality data and the hydrology data tie together to tell you a story. And so if we look at the PO4 loads, those were actually still highest in the grass condition compared to the other two conditions, which I found was really interesting, that even the unvegetated wetland condition was pretty decently below the amount of PO4 conveyed by the grass condition. So another interesting thing to glean from this. So in conclusion, greater annual sediment and total phosphorus loads were conveyed by the unvegetated wetland ditch than the other two conditions, which is likely due to the runoff exposure to bare ditch soils, post-management. No surprise here, if you leave a ditch unvegetated, there is bound to be some, sediment running off. However, the grass ditch still generated the highest annual PO4 load out of all ditch conditions. So, even though the unvegetated wetland ditch conveyed sediment, it still wasn't necessarily the biggest polluter in terms of PO4, which is a bit unexpected, but interesting conclusion. And so in conclusions, looking at the wetland conditions themselves, wetland conditions conveyed 3 to 4 times less TSS annually than both grassed and unvegetated wetland conditions. And therefore, swift ditch revegetation is critical post-maintenance in order to optimize your sediment and PO4 load reduction. The wetland ditch, by far outperformed both grassed and unvegetated wetland conditions, and kind of shows that if you are able to get ditches to these conditions, and especially if you're able to revegetate it, there's actually beneficial water quality. There's good water quality benefits by having this wetland vegetation. And so, especially in terms of dissolved phosphorus, we want to make sure that when we are doing maintenance on these ditches, that we're revegetating so we can get back to the wetland condition that effectively seems to reduce PO4. So as a recommendation, again, I recommend that recently maintained wetland ditches should use simple management changes to reduce the sediment load being conveyed downstream, whether that's a check dam or just a small energy control device, just something to maybe even temporarily slow flow in the ditch to reduce some of that sediment being conveyed downstream. Check dams are a good potential use for, I guess, a potential something that could help water quality in these unvegetated wetland ditches as well. And I guess as a result, looking at the big picture, roadside wetland ditches themselves convey less sediment, total phosphorus, and dissolved phosphorus compared to a standard ODOT grass ditch, and should be considered as a best management practice. Unvegetated wetland ditches, we showed that there are negative consequences of maintenance on these wetland ditches. However, the potential benefit in terms of sediment and nutrient reduction that they offer, really outperforms the typical ODOT grass ditch. And so I think, they definitely offer some water quality benefits at really no cost at all, or very low cost. So definitely should be considered as a best management practice. So in terms of final conclusions for the whole project, roadside wetland ditches offer an extremely low cost best management practice that is effective at reducing sediment and runoff compared to a traditional roadside ditch. Managing this accumulated sediment occurring in wetland ditches can be then simplified by using an easily accessible agronomic soil test, the MANIC3 soil test, to test for sediment, for phosphorus and sediment content above 60 milligrams per kilogram. And these unvegetated wetland ditches should implement simple control structures to encourage sedimentation and runoff and ensure that they're revegetating faster to the wetland conditions in order to optimize the water quality benefits. Acknowledgements. I'd first like to thank ODOT for the opportunity to complete this research. I've really enjoyed every step along the way, as well as the assistance of my technical advisory committee, who are all very supportive through this process and allowed me to ask questions and be curious, which is always a good thing. So I'd like to thank John Pryor, Matt Perlich, and Matt Raymond. Would also like to thank my advisors, Dr. John Witter and Dr. Ryan Winston. I don't know what I would have done without their guidance, and yeah, I don't think there's any better people I could have learned the ropes from. So very, very thankful for them. And then I want to thank Dan Mecklenburg and my undergraduate assistants, William Fiorentino and Sophie Pajak, for their invaluable assistance during field work. Anyone that's ever done field work knows that it's good to have good helpers and good assistants and good people around you. So their help was definitely invaluable, and it made field work, all the more fun for me. So, these are all people that that helped me along the way, and I'll always be grateful for their help throughout this project. And with that, thank you everyone for listening, and I'd like to open it up for any questions.
Wonderful. Thank you so much, Ben. Yeah, if there are any questions, please enter them into the question panel so that we can have Ben share his knowledge with us. So far, Ben, we do not have any questions. You must have shared all of the information and answered all of the questions as you went through the presentation.
Oh, there was a lot of content, so I don't blame them.
That's awesome. Yeah, no, that's great. Let's see here. We'll just give another moment just in case. And you did have your, you said that people could reach out to you also if they did come up with any questions or have any follow-up. Okay.
Yeah, I'd be happy to answer any questions. I have no problem talking ditches, that's for sure.
Fantastic. Well, then we'll go ahead and throw that out there for our listeners, that you may reach out to Ben if you have any questions moving forward. And I will go ahead and say that on behalf of LTAP and ODOT, I'd like to thank you, Ben, once again for sharing your valuable knowledge and expertise with us. And as I mentioned earlier, the recording of this webinar will be shared with all registered attendees. So thank you so much, everyone, for attending. We hope you found this webinar informative and engaging. And I wish you all a very wonderful holiday and a wonderful rest of your day. Thanks so much.